All right, good morning, everybody. Today is Monday, October 28th, 2024, and we have a new section open in ES 1060, and this section is going to be on graphing. Before I get started, I would like to invite you to see a demonstration and to hear about some job opportunities that are available to you, and also to have some pizza and refreshment with some of your classmates. So tomorrow at 2:15 p.m. in the drafting lab, an engineer by the name of Kyle Wolf, who works for Anvil Engineers in Billings, is going to come down and talk about some opportunities that are available to you, both in engineering and in drafting. So I think it would be worth your time to come see what Kyle has to say. If you're not available at 2:15, come at 1 o'clock in SM 104, which is the lecture room across from the physics lab, for the same information. So hope to see you tomorrow. And we'll talk about, like I said, some opportunities that may be available to you as an engineering or drafting student. All right, so today we are going to be talking about graphs. And before we get going on what Excel does in graphing, I would like to take a few minutes and talk to you about what graphs, the purpose of graphing, and also how to do a good graph and how to do a bad graph, because good graphs and bad graphs are only separated by a few things. So the purpose of a graph in an ideal world is to present information in an organized manner. Sometimes the evil purpose, put evil in quotes, is to misrepresent or to lead people in an incorrect direction. So as engineers, we are always interested in creating good graphs. Advertisers are the primary people who like to do misleading graphs. And if you look at something that it's a bad graph or a misleading graph, it's not overtly a lie. It's just something that is designed to pull you in a certain direction rather than rather than toward the truth. Now, how this can happen and why graphs are so powerful when it comes to misleading you is because you may have heard the phrase somewhere along the line that a picture is worth 1,000 words. I have to turn my phone down, sorry about that. And a picture is worth 1,000 words. What that basically means is that to a human being, visual information is very powerful. And if you do not analyze a graph, if you just look at a graph, your nervous system actually processes it in the same areas as it processes pictures. So when you see something that's misleading, it's very human to be misled by the misleading presentation of data. So these are some old graphs from 2007, so approximately 17 years ago. And what we're looking at here is numbers of sunspots and reconstructed temperature. So this is like temperatures of the Earth over time, all right? Now, if you take a look at these graphs, you'll see, for example, the reconstructed temperature. If you take a look at medieval warming period, which is when well, that's a long story. There's many, many interesting historical antecedents that go along with this and correlations. But in the 16, 17, 1800s, there was this little ice age, which meant that the temperature was quite a bit lower. And now in 2004, or now, she says 20 years ago in 2004, the temperature had become much higher. So if you look at this graph, it looks pretty dramatic. As an engineering student and a person who studies math, what do you see about that? It's, first of all, the data on this is pretty much true, but what do you see about this graph that might mislead you, or that might lead you to having a stronger emotional reaction, which is really what misleading graphs attempt to do? What do you think you might see?
Looks like it's too much, gathering too much data.
Right, okay, good point. The first thing is, let's take a look at this and pull it through. It talks about reconstructed temperature. First of all, that is true. What does that mean? Well, that means that back here in the year 1100, they really did not have terrifically accurate thermometers. So they had to reconstruct this from, they didn't have any thermometers. So they had to reconstruct this from natural data, like rings in trees and journals that people wrote. And if people, there were not very many literate people in 1100, but any amount of written material, but mostly natural history, polar ice caps, drilling ice cores, looking at crop records from different years and so forth. The other part is, aside from the fact that how do you get the data here, look at the scale on the vertical axis. This is a temperature anomaly, okay? And if you notice, we're talking about degrees centigrade, but we're not talking about an actual temperature. We're talking about how different it is from a standard, which we set at this reconstructed temperature of 1000, of 0, meaning that's what we're using as our base in the year 1000, okay? So what we're saying is that if there's no temperature variation here, they're actually taking that during a period of warming. So what they're doing is they're comparing the 0 to a period where it was already warm. For whatever reason. As we continue downward, we see that in this little ice age, there's many lines, and this particular graph doesn't even tell you which line means which. But if we sort of look at the middle of it, we see that during the little ice age, that we were down about half a degree from this 0 period, and that here in 2004, which we can see has peaked up very significantly from, here's 1900, here's 1950-ish, and here we are in 2004. We're up about less than half a degree from that base again. So if we really made this graph where the axis on the left was of a different interval, this graph might look very, very flat. Now, it really does look like, and it is true, I'm not a climate change denier by any means. I just want you to be, I use this because this is an engineering issue. Climate change is an engineering issue, a scientific issue that has been highly politicized. So you see a lot of misinformation on both sides of it, both on the fact that global warming is a ruse and global warming, we're all going to die in 10 years. You know, I mean, the truth is somewhere in between. But the part that I would like you to see is the temperatures were very stable until about 1950. Well, what do you think might have happened in about the mid-1900s? People started living differently than they had in the past. Okay, really it started happening in the early 1900s, but like in 1940, if you think about living in Powell, Wyoming, or anywhere in the Midwest or the Western United States, there were very few cities or towns, and certainly not very many rural areas that were even electrified until 1940s. The REA, the Rural Electrification Act, was published in, I think, 1938 or something, and the first REAs came around well, not the first, the majority of REAs came about in like the 1930s. So when we started burning coal for electricity, we did have some effects. We also had gasoline that they put, lead in. Lead actually, is a lubricant. It's an industrial lubricant, keeps all the seals nice and, mushy in your car, anything that's made out of rubber. However, it also is it's a heavy metal and it's a pollutant. And so putting it in gasoline and burning it is kind of maybe a terrible idea. So, there's a lot of things that go into this, but the one thing that this graph does not say is the temperatures are skyrocketing and we're all going to die in 10 years. It also doesn't say nothing is happening. So those are just some interesting correlations. Now, here's another, global temperatures. This one starts in 1860. And I think this is kind of interesting, because if you think about on this graph, 1860, that's right here, all right? And that was at a low peak, at a time when the temperatures were globally low. Now, they did not know this at the time, but there's a year in there that they called the year without a summer. And they also called it, in New England, they called it 1800 and froze to death, because it was basically just cold all year. Well, what had happened was there had been a major volcanic eruption that spewed a whole bunch of particulate matter into the atmosphere. They didn't know that. All they knew it was cold and their crops didn't make. But there was a big volcano that blew up. There was a whole bunch of particulate matter that went into the air, and until it calmed down and settled, there was basically a humongous decrease in the amount of sunlight that impinged on the world. So that was sort of what happened. But if you compare then to that year, 1860, which was when this happened, you'll see that in 1910 or so, there was another trough, or another actually lower than 1860. Let's do something here because we have Google. I'm going to put in the year without, what would I search on? A summer, which is 1816. Okay, and there it is. And there's some stuff I couldn't bring to mind. Mount Tambora in Indonesia erupted in 1815, and away you go. All right, so actually 1800 froze to death isn't even on this graph, but it's down here somewhere. Let's see if it'll tell me what caused a dip in global temperatures in the early 1900s. Let's find out, because I don't know the answer to that. What caused global temp to dip in about 1910? Massive ejections of sulfur dioxide particles in atmosphere are thought to have caused a drop of 1.2 degrees in northern in the northern hemisphere, again primarily due to volcanic activity. Well, once again, if you were a farmer in Vermont or Maine or Boston, the Boston area in the 1800s or in 1910, you may have more information, but there's still not a lot of information. So all you know is that things are just really cold. So anyway, and if you look at these global temperatures, here we are, this would be 1950, right? Where we sort of have this dip, where we sort of industrialize and have electricity and coal generation for a lot of different people, and the temperature goes up. But once again, if you look at this scale on the left hand, you're only talking, here's your zero, right? Now this looks like a more accurate zero because it looks like about half of the data is below it and half of the data is above it. That's better than this one, where my zero is up here for some reason. You know, I would expect the zero to be like in maybe in this area, but that's another story. But here you can see once again, there is this truth that in about 1950, global temperature started to go up a little bit. All right, it's one of my favorites because it's silly. The number of misleading graphs used to defend global catastrophes, and they just say they're going up. That's just a silly graph. But there's a lot of misleading graphs in this world. And so as an engineer, one of the things that you really need to do is to A, don't let this happen to you, and then B, I love this one too. And then B, analyze the graph. Don't let it hit your head like a picture and then believe it, because, you know, it's like, I watched a presentation, gosh, 10 years ago or 20 years ago, that Al Gore had put on about global warming, and he was sort of the evangelist of global warming. Well, I guess I'll just leave it at that. But there was a picture at the end of the presentation that I saw, which was a mama polar bear and a baby polar bear floating on a little piece of detached ice. And the baby polar bear looked sad in the water. The mama polar bear was trying to get it. And that really is like, that's a really sad picture, but there's some evidence that maybe it wasn't even really what they were saying it was, that it was something else. And, but it really got to people because it's a picture. So here's another picture. This is one of my favorites. I was looking at this, and this is a type of a graph called a pictogram. And a pictogram is particularly good at lying to you. I mean, oh my gosh, so good at lying to you, because this hits all those nerve receptors, or all those brain receptors, all those, it opens up all those synapses of a puzzle. All right, so of a picture. It is kind of a puzzle too. But so basically, my mother-in-law brought me this picture. It was in something out of a retirement journal. And the basic message of this graph is, as you get older, you need to eat more protein, because protein will make you stronger to an older age. So you see, of course, there's some guy, he doesn't look all that fit to me, but you know, he's wearing glasses and he's got a comb over, and I don't know if he's the guy that I want to aspire to as I grow older, but there he is, just the same. But he's strong, right? He's lifting weights, so he must be strong. But what they're saying is, here are some different sources of protein. And if you read the words, it tells you that men should get about 56 grams of protein a day and women should get about 46 grams of protein a day. And then it lists some grams of protein per different amounts, different types of food, and then how much it costs per gram of protein. Now, the per gram of protein is an interesting one. And this is old data. I don't have any idea what the cost of protein is now. But look at the first two numbers. 1 cup of chicken compared to 5 ounces of salmon. Well, a cup of chicken is obviously the best, right? Because it's 43 and it's at the top. Well, how many ounces are there in a cup? Depends on what kind of a cup, right? Because we're the United States, but basically 8 ounces is a cup. So 8 ounces of chicken versus 5 ounces of salmon have, within 2% margin of error, the same amount of protein. Salmon is more expensive, obviously, but you don't have to eat as much of it if you don't like it. The other thing is, not really like, I can't even explain how seldom in my life I've ever measured chicken in a cup. I mean, I have trouble even understanding what that looks like, but you know, but there you go. So we have a cup of turkey, a cup of soybeans, and then here we are. So we've got cups, and then we're down to 3 ounces of roast beef. Well, 3 ounces of roast beef obviously is not as good as 5 ounces of salmon, right? Because 3 ounces of the roast beef only has 26 grams. Well, once again, we have a problem here, because that's 3 ounces versus 5 ounces. So if we take the 26 and multiply it by 5/3, we get that 5 ounces of roast beef, if we were comparing 5 ounces to 5 ounces, actually has 43.3 grams of protein. So once again, it's a weird comparator, isn't it? So we start with the most based on what we've decided is a serving, I guess, a cup of chicken, which, even though I don't measure chicken in cups, that's an awful lot of chicken. You're gonna want to eat some chicken if you're eating a cup of it. But then you see the pyramid gets smaller toward the top, I guess because it's better, or you're getting closer to being the fit guy at the top or something like that. I don't know. Anyway, then we got 3 ounces of ground beef, blah, blah, blah. And we come down here to some of my other favorites. Here we go, a 1/2 cup of ice cream. Well, that has 3 grams of protein. That means that if you needed to get if you need to get roughly 50 grams of protein, you'd have to eat a lot of ice cream. And apparently there's no value judgment on this as to what else ice cream has in it that is probably not a super idea to be eating tons of that. A tablespoon of peanut butter, eggs, nuts, cheese, tofu. Tofu is a great source of protein I used to eat a lot of it because it was cheap and it was when I was in college, but it's not necessarily the most palatable form of protein for a lot of people. But I just think it's a really interesting thing because you have things on here like meat, and if you normalize the meat to the same standard, most meat has about the same amount of protein, whether it's turkey or ham or chicken or beef or fish. Turkey, ham, chicken, beef, fish. It all has about the same amount of protein. It has other things in it that you want to vary your diet because, like, for example, if you love fatty fish like tuna, mahi, and so forth, they're really delicious. They're really high in protein. They're low in fat, but they also can be very high in mercury. So you need to be careful to not, because things concentrate in the ocean, and so just the way that they're raised, you have to kind of be careful of that. But if you ate an ounce of cheddar cheese, if you were going for 50 grams of protein and you decided you were going to get it all by eating cheddar cheese, you'd be eating a lot of cheddar cheese and you'd have some other health effects as well. So all I'm saying is these graphs can be useful. What's useful here to me would be the data. It's like when I was going to decide if I was going to try to make myself have 50 grams of protein a day, I would have some different sources so that I wouldn't just be going to a can of tuna fish every day or whatever. But basically, you have to read through the data and you cannot necessarily just take it as a picture. You have to analyze it as a source of data. Now let's see, I'll show you one more if I can find it. Oh, this was some job stuff. There is some really good stuff about, let me see if I can find it. I don't know if I can. Powell High School had sort of inadvertently, in my opinion, put out some problems with some ACT data. And first of all, I would start by saying that, here it is. Powell High School has really good ACT scores. This is from several years ago, but you can see how happy everybody is. So that's the most important thing with the high school pamphlet. But on the back of this pamphlet, or on the front of this pamphlet, they talk about core ACT scores. And there's a couple of things that are really interesting here. First of all, I want to start by saying Powell High School has really good ACT scores for college readiness. Did you go to Lovell High School? You guys have it better. So you guys ACT scores are really good. But there is a huge problem with comparing different school districts and ACT scores. And first of all, I would say as a college instructor, your math ACT score is my most reliable indicator. That's just from me teaching. Nobody said this to me, but that is my most reliable indicator of what math you're ready for and where you are in terms of your college readiness to study engineering. However, the biggest thing when you look at a school and you aggregate ACT scores is some schools pay for the ACT score and require students to take ACT. Other schools, they pay themselves and you self-select whether you want to take it or not. And some schools take a different test, which is the SAT. Well, the schools in the Bighorn Basin, and I'm pretty sure all of the schools in Wyoming, pay for students to take one round of the ACT scores. And so what that does is people who are not really going to college and people who are not like studying and excited or dedicated to doing well on the ACT also take the test. So oddly enough, when a school district requires everybody to take the ACT or pays for everybody to take the ACT, the aggregate ACT score of that school goes down. So it's kind of like a slippery slope, isn't it? You know, I mean, it's still good data, but you can't compare it to a school district where everybody self-selects and only takes the ACT if they're going to go to a school that wants ACT versus SAT scores. All right, so here's the other part that I just love. ACT scores here are core scores, okay? So when they talk about core scores, what they're really talking about is college readiness. So students who took these classes, they did not take, so in other words, they took standards 1 or 2 math, which I think has been relabeled pre-algebra or algebra half, standards algebra, college prep math, okay? So they don't include people who take those math courses or people who take environmental science, physical science, or geoscience. So they're only capturing the kids who are doing hard math and science, and then they project their ACT scores. So it's an interesting way to try to normalize the data, but I can't help but thinking it's also trying to normalize it against people who made 15s, which is the minimum you can make on an ACT test. So what you see then is they have these different averages for these different years. And once again, this data is a little bit old, but we have 2004 or graduating in 2005, 6, 7, and 8. Okay. So if you look at that 5, 6, 7, 8, 5, 6, 7, 8, 5, 6, 7, 8, it looks like the students that graduated in 2006 had a pretty significant bump, and I don't really know what that relates to. And then it looks like maybe we're a little up from the average in 7 and 8. So it looks like we sort of we were down a little bit and then we came way up and then we went back down. But if you look at the 3 years, eliminating 2006, we're sort of on an upward slope. So that looks pretty good. But here's the other thing. Look at the scale over here. We're only going from 20 to 26. Do you know what the top score on an ACT is? 36. So we don't have anybody up here, right? I mean, what we're saying is, well, you're not even going to get to that average, but really, if you're going to compare it to something, we didn't start at the bottom either. This scale should go from 15 to 36 if you're going to show a good graph, right? So those are just sort of some of the ways that you can make data look different than it is without lying about it. I want to be really clear. This data is not lying. It's just, if you accept it as a picture, you're going to see something that's really not there. Okay. So when we start working with Excel and graphing, one of the things that's really, and this is actually something that I think is really interesting, MATLAB graphs very, very well also. So, but there's a bunch of different ways to create graphs. And basically, if you pull up an Excel spreadsheet and you take a look at this is getting the data. Creating a chart. That's what they call it. They call it charts. That's right. So you have to find the feature that talks about creating charts, which is right here. It's under the insert tab on the ribbon. And you have different sorts of charts. And if you hover, you can see what those different charts are and how you can display them in Excel. And these are only some recommended charts. There's a boatload of charts. Pivot charts are something that you'll become very interested in. That's something that engineers tend to use a lot. Bar charts generally compare things, just like we just saw some bar charts with the ACT scores, where those are called clustered bar charts, where you're looking at different years of data, but you're looking at different things within that data. So it's a really good way to organize that. And then, of course, there are scatter charts. Some other things that you will learn in Excel, and we will have lab this afternoon and work on this, but one of the other things that you'll learn about charting is that if you're looking for trends, like you want to see if something is increasing in a certain fashion or decreasing in a certain fashion, if you have a graph like this and you start at 0 and you have some Y value here and you go to some X value here, but you have a true 0, an origin of your graph is 0, 0 point. If the graph if the graph looks like this, if you plot the data, you can curve fit to a line that goes through it. And if it's a straight line, it will follow that formula for a straight line. Y is equal to mx plus b, where b is the y-intercept, m is the slope of the line, and then you can determine any y point from any x point. Okay. Also, this is the independent variable and this is the dependent variable, the way I have this drawn, because basically you take this value and then you calculate this value. So you can find what you would expect it to be based on that. Now, you don't always have graphs that look like that. Sometimes you have graphs that trend in a different way. So once again, if you have a 0, 0, some y and some x, independent and dependent, maybe the data curves like this, or maybe the data curves like this. This might be something that would happen for like the growth of bacteria, because basically bacteria multiplies, and if you have like 2 bacteria, it turns into 4, and then 4 turns, each one of those splits and turns into 8, and then 16, and so forth. So it doesn't increase in a linear fashion, but it increases in an exponential fashion. Sometimes you can change the axis to sometimes they call a semi-logarithmic plot, where instead of being linear 1, 2, 3, 4, 5, you might have 10, 100, 1000, or 10 to the first, 10 to the second, 10 to the third, and so forth. And if you plot it that way, sometimes this sort of data will kind of look like a straight line, and then you can develop a trend line based on a semi-logarithmic plot instead. Or there's also log-log plots, which are kind of the same, except you plot logarithms on both axes. And sometimes you can find a good trend line on that as well. Something that the data doesn't look that way, but it will normalize or linearize on either a semi-log or a log-log plot. And Excel makes it extremely easy for you to compare those things so that you don't have to draw it out by hand and then give it a shot. You can make that determination. So finding a trend line, especially with really naturally occurring data, is a big deal. One thing that kind of just to finish up here, whenever you collect data will almost never fall in a perfectly straight line. So what you try to do is some sort of a curve fitting, which Excel also will help you with. But basically you're saying, well, I have a few points above and below. So I draw a trend line that somehow balances out what's above the line and what's below the line. And then if I get a real stinker or an outlier of a data point, it will identify that and kind of throw it out. So outlier is just a piece of data that, I don't know, you went to sleep or something, you were measuring the weight of beans and you accidentally put a sandwich on the scale or something like that. And so you get a bad data point. And it happens. So you need to be able to, you don't want to say, if you have this stinker point over here, you don't say, oh, my trend line looks like this, and then I've got all this data up here and one single data point below, because that's not a good use of the analysis of using graphs. All right. So at this point, do you have any questions? Chapter 5 will step you through this very, very nicely. The exercises are super. And putting graphs immediately into a spreadsheet is, I don't know if I would say easy, but it's really effective, and it's a great function of Excel. Like I was saying, we're not going to go back to MATLAB, but MATLAB also creates graphs very, very easily. So if you're ever programming, we didn't get into that because I wanted to get into Excel more quickly and spend more time over here. But if you are graphing, if you're using MATLAB, check out the graphical formulas in MATLAB, and I think you will be extraordinarily pleasantly surprised at how easy it is to create a graph. One line, maybe two. You fill in the axes, you fill in the scales, you fill in the colors, you fill in the legends, everything. But so my basic advice when we're talking about graphs is, as a consumer of data, analyze the graph, don't accept it as a picture. And as a creator of graphs, don't mislead anyone. And that's how we do some good engineering communication with graphs. All right, any questions today? Well, all righty then. I will stop the recording and then I will be over in the lab this afternoon. So I'll look forward to seeing you then. And in the meantime, have a great day.